Geometric sequences is what we're going to be talking about. What is an arithmetic sequence? What
Addition
defines
and
it?
subtraction.
What defines it, though?
Addition. What do you mean define?
What, if you look at a sequence, how do you know it has to be arithmetic?
There's a pattern of adding or subtracting.
Okay? So it has a common difference.
There's a common multiple.
So, when you talk about geometric sequence, our definition is a sequence with a common ratio. Meaning, you have some term divided by the previous term is equal to r. So you choose any two terms and you'll get the same r's. Any two terms in the sequence. So let's say if we start with, say,
3,
4, 12, 36, 108, 324, and so on. Because any term divided by the previous term, we should get the same answer.
3.
So 36 divided by 12, 12 divided by 4, 324 divided by 108, 3. So this is what we mean when we're talking about a geometric sequence. Now, of course, there are some standard formulas for it. So first, let's do the recursives, and that's an easy one. A1 equals C, some constant we're starting at. How would we get to the next term?
A1 equals AN minus 1 times the D. That is R.
R times AN minus 1. So we're just taking whatever our previous term was, multiply it by our common ratio.
How do we know the combination?
We can find it like this one, 36 divided by 12.
No.
12 divided by 4.
Don't tell you that.
Then you're told the common ratio, or you're told two terms. So explicit, what would the explicit form look like?
AN equals something to the power.
Okay, so how are we going to have something to the power? Okay, notice when we had an arithmetic sequence, we had repeated multiplication, right? Or repeated addition, which means that we change it to multiplication. Here we've got repeated multiplication, which means we're going to change it to exponents. Let's think about this. What do I multiply this one by to get to the next one? 3. So I'm going to put times 3, times 3, and 3. So how would I get from here to here?
9.
Oh, I'd have 4 times what?
36 or
3
108?
to the, yeah, to get 108.
Oh, 2 to the third.
3 times 3 to the third.
Which is 27.
Okay? So this is fourth term, third term, second term, first term. So now, how would we translate that into
AN.
So, what does 4 represent?
A1.
A1. So we're going to have A1 times
R.
R raised to the N. Does this work?
Oh, sorry, minus 4. Or, no, minus 1 now.
So if we wanted a fourth term, we had to plug in 3 here, right? If we wanted a fifth term, we'd have to plug in 4. So this is our general form of an explicit form function. It's a geometric. So, how would you write the explicit form of it? Given two terms, A1 equals 5, A3 equals 8.
What do you think? What are we writing? The first thing?
Yeah, well, either way. I thought you could do both forms.
A1 equals 5.
Okay, A1 equals 5 right there. A3 equals 80.
minus 1.
Okay, so where we starting at? Oh, just put R. Raised to what?
R squared.
R squared. Okay, and what is A3 equal to? 8. And how would we solve it?
Divide it by 5.
Divide by 5. Therefore, 16 equals R squared.
Therefore,
R equals
plus or minus 4.
plus or minus 4. So we've got actually two different sequences that we generate. If R equals positive 4 or negative 4. So what would let's do recursive first. What would A1 be?
5.
Okay, and AN.
Plus or minus 4.
So I'm just going to do 4, and then we'll do an alternate, give the two possibilities.
Or times A and minus 1.
Or we could have it's either this one or this one.
How do you write it?
What? No.
How would you write it?
We say or A1 equals 5, AN equals negative 4, AN minus 4.
Why can't we just say plus or minus 4 A?
I like this notation, that's better. If you are talking about two separate sequences. If no, if you did A4, you'd have different answers depending on which sequence you had. So you could do it that way. How would you do explicit? Or yeah, what do you think a conversation people do with this when they're if I ask you to find me the sixth term of it?
They do 4 to the 6.
No. Not that I made a mistake. Probably the most common one. The 6 minus 1. What do you think the most common is?
From 5 to 4. And that's
Yeah.
9.
Between 5 times 4.
Why would they do that?
Because they're not following the order of operations. But and these look it's so inviting. 4 times 5 that's such an easy number. And then they try raising it to the 6, and that gets much more complicated than trying to do 4 to the 6.
It won't be the same answer.
No, it won't. Because you're doing the order of operations wrong. Yeah. We also might want to sum up a geometric sequence. Right? Yes?
What is sum up?
We want to add up all the terms of the sequence.
Oh, the thingy.
So, actually, with this class I tell you about the chessboard problem where you're putting one rectangle array. No? Okay. Oh, it was ancient China, I think it was, maybe India, where the king hired off the Gothic architect said, I want you to build me the most glorious palace ever made. And he said, okay, I can do that. And the king said, so what's your payment going to be? After they were playing chess, he said, hey, you've got chessboard, I want you to put one grain right in the first square. Second square, 2, third square, 4, fourth square, 8, and so on. Is that fair? Correct. So we have the terms 1, 2, 4, 8, 16, and so on. How would we add up? So how many squares are there on the checkerboard or chessboard?
32.
No.
64.
64.
Okay.
So we want 64 terms added
Oh,
together.
yeah, 8 to 8. What?
So how would you write the equation for this first?
So what are we trying to find?
1 times 2 to the n minus 1. Since this 1 isn't doing anything, I'm going to erase it. So I want to add up the first 64 terms of this. So n equals 1 to 64 of 2 raised to n minus 1. Anybody want to do this by hand? Okay, so there's a nice formula for it. Sn. So for a geometric sequence or series, Sn equals A1, 1 minus r to the n over 1 minus r So what is the first term of the sequence?
1.
So we have S64 equals 1. 1 minus, what is 2 to the 64?
You tell me.
I don't know.
How don't you know?
What?
You should know.
No, that's a bit too big.
Trillion.
One, tell me that's what they want.
Let's see. So we're going to do, this is scientific notation, 1.84 times 10 to the 19.
Is that close to trillion?
It's much, much more. Over 1 minus 2. And it is a bit more than this, so somebody do that on your calculator. 1 minus this divided by negative 1 times 1. Yeah, see if we multiply by
It's going
1.
to be negative what?
1.84 times 10 to the 19. So let's see, 184, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17.
What is after
Technically,
trillion?
would,
So,
if you're using the, like with the help rounding, if you're using the 1.84, it might just be a big string of 9, 6, 3, a lot of 9.
but no, I'm just rounding there. So they've got millions, billions, trillions, quadrillions, quintillions. So 18.4 quintillion grains of rice.
What's after quintillion?
Now, how many grains of rice are produced in the world annually?
A lot.
A lot less than this. This is a bigger number than all the grains of rice that's ever been produced in the history of the world. Because that's the standard staple for food.
We eat a lot of rice.
This is a very, very, very large number.
How many grains of rice
This,
turn a pound back of rice?
maybe a million, a billion, maybe. Probably less than a billion. Probably, I'm guessing a million. But maybe even less than that. I don't know. But this much rice might even be something the size of the moon. I'm not positive, but you're talking. This is a huge thing.
Cooked rice or not?
It doesn't matter. This is a massive, massive amount. Of course.
If it were cooked, it would probably be
I have a question.
Yes.
What's after quintillion?
Sextillion,
What?
sextillion,
And then?
septillion,
And then?
octillion,
And then?
nonillion,
And then?
decillion.
And then?
I'm not sure.
Oh, so it goes by the quin and then the hex and then the
Oh,
sex,
it's sextillion.
sextillion,
Yeah,
and then the septillion, octillion, nontillion, and
nonillion.
nonillion.
So it's not like septillion.
Okay. So we can sum up any geometric sequence we want to a certain point. But what if we wanted to sum up the entire sequence?
Like infinity?
Yes. So for example, if we did this one, the sum n equals 1 to infinity of 2 to the n minus 1. What is it equal to? That was an infinite sum.
That's easy.
However, we don't always get infinite sums.
Like, give me an example.
Okay? Let's consider this one. 1, 1/2, 1/4, 1/8, and so on. And we want to add them all together. To add up the entire sequence. So, consider if this is 1, because this right here would be another 1, right? So I'm going to say we're adding up this whole thing, that's our original 1, plus half of 1, which would be like this amount, right? Plus 1/4, which would be here. Plus 1/8, which would be here. Plus 1/16.
That'll be 1. That'll be 2.
Plus this one. Plus. And keep repeating this over and over again to infinity.
That'll be 2.
We add them all together, we get 2. So this one, we can add up an infinite number of numbers, and we don't get a infinity. We get 2. Okay.
What if it was, I forgot, what if it was the arithmetic? The one that we-
Arithmetic?
Yeah,
And it depends.
what are the limits?
There's an interesting formula. N equals 1 to infinity of n.
Why?
Did you watch the video about that in this class?
1 plus 2 plus 3 plus 4 plus 5 plus that equals -1.
If you have an infinity, yes, it's negative 1 plus. Did you watch that one in this class?
No, really.
Okay.
Can you explain?
It's an interesting problem.
That's true. Who said that?
Mathematics does it.
Mathematics says when you add a positive number, it can't be a negative number.
Well, we can if we go to infinity. And
How?
Well, maybe tomorrow we'll watch the
No,
video.
no,
about
I
that.
want to know right now.
Okay?
I
So,
need to know right now.
yeah, the thing is, infinity has interesting quirks. The thing is, this is also used in physics. This is a quantum physics equation. It's like at the beginning of your textbook. It's an introduction. The sum of 1 to infinity is negative 1/12.
That's true. Who said this? Wait, who said this?
What do you mean you said it?
Does it make sense?
Yes.
It makes sense?
No. Actually, there's no good reason for it.
Who said?
But the mathematics says it works.
Mathematics says it doesn't.
No, there's not.
They like to.
It's like this, and it's like in charge of the universe, like we go to party too. Why? Just
Now, if you want an infinite geometric sum, S is equal to A1 over 1 minus R. 4. In other words, if our common ratio is 1, or less, 1 or more, this won't work. But if it's less than 1 and above negative 1, we can use it.
What are you saying?
So if our geometric ratio, so for example, let's say this is 6 times 3, 4, the n minus 1. Okay, what is the common ratio in this theory? What's the common ratio? Here? 3/4. So is the common ratio less than 1? Okay, then we can use this sequence, this thing to add it up. So this is equal to, what is A1? 6. Divided by 1 minus 3/4. 6 over 1/4, which is 24. If we added this over and added it up, we would eventually get 24, we would get infinity.
So this is only when R is less than, let's say,
For the absolute value of R less than 1.
what is this greater?
Then it's infinity. This infinite sum doesn't come to a set point.
So the other one, wait, is the other one good for anything, or
Would
the
be-
one
oh.
for RCN overall, or does that work for anything?
Yes, this is for if we want int terms. Okay. Because if we had, for example, I said negative 3/4 here, it's still 5. That's why.
Still less than one.
That's the value lesson. Whereas, if, for example, if I put at negative 2, this would not work.
Why wouldn't, oh, yeah. So if that was negative 3/4, will it be 1 plus 3/4?
Yes.
It will be 7 to the 4th, 6 to the 7 to the 4th.
6 divided
So it
by...
will be 24 over 7.
So, homework, relatively easy.
Are we done?
Yeah.
Can you explain the thing?